All right, okay. Hello, everyone. Good afternoon, good morning, or good evening, wherever you are. Ayan, hello, and welcome to our first of our webinars for this year's ICT month. Hoot, hoot. Ayan, okay. So, before we start, I am Jabez Aison. So, hindi ko na lang na-rename yung sarili ko sa Zoom, but I am Jabez, currently the Director of Operations and Community Growth at the Quantum Computing Society of the Philippines. And also, I am an AI intern here at DOST ASTE. First day ko actually. So, ayan, medyo ano pa. Medyo kinakabahan pa. But yeah, um, so yeah, thank you guys for being here with us. So just like me, I'm sure na you sign up for this session because you are as interested on the future of ICT. And we believe, no, KCS, we believe it's quantum information, science, and technology. So before we begin, now let's have like a short icebreaker muna. So if you can open your phones, ayan, or your computer or whatever device you're using, and if you can go to menti.com, ayan, so hopefully you can see my screen. Ayan, menti.com, and if you can enter the session, yung ating code ay 41672083. Again, if you can go to menti.com and the code is 41672083. And siguro you can start answering na. Ayan. So if nag-load na, ayan, may tatlo na sa ating, ayan, may apat na sa ating menti. My first question to you all is, since it's literally the ICT month, what is your favorite ICT sector or field or fields, no, kung meron kayong maraming interest? Napakarami yung time. Sana all, no? Pero if marami kayong interest na field or sector, maybe you can share on here. Ayan, I think pwede kayong mag-share up to three or more as well. So it can be like AI, it can be quantum, or it can be other technologies like web development, edge AI, edge computing, yung mga ganoon, sensing, IoT, ano pa ba? Ang dami, napakaraming mga fields na or sectors ng ICT. So yeah, if you can share and we can see, ayan, yung ating word cloud. So we can already see deep learning, wow. And AI, ML, data science, back-end development, and we have DBMS, na database management systems. Ayan, palaki ng palaki ang AI infrastructure, quantum computing, wow. And ayan, I think may nadagdagan machine learning. Ayan, lumaki yung AI, data analytics. Ayan, mga magkakapatid pala yung mga interest natin. No? Game dev. Wow, there's someone really interested in game dev. That's cool. Ayan, how to be you po. Ayan, naglalaro lang ako, pero I can't phantom how to create games. Oh, yan. Okay, so as you can see, most of us are interested in AI, machine learning, data science, data analytics. Oh, blockchain. Wow, cool. Dalawa sa blockchain. Woot woot. Represent, represent ng mga Web3 and blockchain peeps natin. Okay, great. Ayan. Okay, thank you for participating. And for our second question, ayan, huwag na kayo mag-leave sa ating mentee. Our next question is, what other words or anong ibang words yung naiisip nyo kapag narinig nyo yung salitang digital and bayanihan? So if you can see yung logo ng ICT Month, di ba? Digital bayanihan. So ano yung naisip nyong ibang words that are related to digital and or bayanihan? So ako personally, hindi, sige, mamaya ko na lang i-share yung akin. Ayan. So ano kaya? Digital. Napaka-techy, no? Kapag digital, talagang ICT City Month. Tapos bayanihan. Napakagandang Tagalog word ng bayanihan. Ayan. So, I'm curious, what do you guys think about digital bayanihan, which is the theme of the National ICT Month. Ayan. Digital community. Wow. Brainstorm. Ayan. Digital community, I think this is on the sense na everyone in the community is empowered. No, modern unity, wow. No, hindi lang siya yung uh, like yung traditional na unity na camaraderie. Na-imagine ko kapag ano bayanihan is yung nagdadala sila ng ano, ng kubo. Yun, 'di ba? Bayanihan, yun yung usually nating naiisip. But sabi ng ating anonymous person, modern unity daw. And yan, technology, pinaka-biggest word of course. When you say digital, it's almost always nakadikit ang technology. And digitalization, ayan, democratization, yun, napakaganda namang word, no? Na everyone has access to digital tools, digital resources, no? Ano pa ba? Collaboration, yes, bayanihan, di ba? You need to collaborate when when you talk about bayanihan. Industries and society. Great, that's awesome. Napakagandang mga words na ating mga nasambit. Nasambit na yan. Great, awesome. Thanks for participating na for the interest of time. We'll move now back to our, ayan, may humabol. Saan yun? Online community building. Ayun, talaga nga naman, no? When we do all this to build something, to build a more united, a more digital future for the Philippines. Ayan, okay. Moving back to our session for today. Ayan, before we go to the talk itself, we just want to introduce ourselves. We are QCSP, or as also known as the Quantum Computing Society of the Philippines, and our goal is to build the quantum ecosystem of the Philippines. So, marami kaming ginagawa. Siguro nakikita nyo kami everywhere. Now, we want to advance quantum tech, particularly sa research and innovation. At the same time, na lumitaw rin tong word kanina to foster collaboration between different sectors, no, sa academia, sa businesses and industry, and even sa government. And one of our biggest bets talaga is to nurture and enable you guys, no, the next generation of quantum professionals. And of course, to promote awareness to everyone, no, na hindi lang ito basta like, oh, okay, may quantum pala, but it's something on the future as well. So, aside from that, we are affiliated with the One Quantum Network, mayroong global network around the world, and QCSP is also the local chapter ng One Quantum Philippines. We're also representative ng Philippines sa Southeast Asia Quantum Consortium, and at the same time, no, endorsing societal partner for the United Nations International Year of Quantum Science and Technology. So we are also in deep partnership with DOST ASTI and DOST Presured for under their quantum, AI and blockchain projects, and sa Presured naman on the Quantum PH program. Ayan, okay. So this is very important, no? Kaya talagang we're hard at work. So if you've seen our posts lately, lecture series and then hackathon on LaSalle, on Iligan, and on Naga just last Thursday, no? Talagang ginagawa namin ito because 2025 is the International Year of Quantum Science and Technology. So this was announced by the United Nations, no? So we acknowledge, no, they acknowledge, and we acknowledge, no, the usefulness and the impact of quantum science and technology on our lives. So medyo low-key lang siyang technology pero napakarami niya palang fields na natatamaan that we are using every day na hindi lang natin na-realize na meron palang aspects of quantum, or our understanding of quantum has helped shape the technologies that we use today. So that is our talk for today, no? Quantum information technology as the future of ICT. All right. So to introduce our speaker, so we have Sir Dylan Josh Lopez, the Director of Collaboration and Partnerships at QCSP. So let me just read or let me introduce him. So Sir Dylan is the Director of Collaborations and Partnerships at QCSP and a research affiliate at De La Salle University, where he supports collaborative initiatives in quantum technology and innovation. He's also a managing partner at Post Quantum Technologies Incorporated, where he focuses on quantum cybersecurity. Aside from that, he also serves as a technical panelist for DOST Assured and a member of the TTI Bureau of Standards on IEC ISO JTC3 Quantum Technology Committee. So Sir Dylan holds a bachelor's degree in computer engineering here sa Philippines and has over 7 years of experience in academia and innovation as a university researcher. He earned his master's degree in computer science and information engineering. And currently, he's pursuing his PhD in electrical engineering in Taiwan with specialization in industrial quantum computing applications for the energy sector. So his recent works include contributing to the NVIDIA developer ecosystem through published blog articles and technical content on quantum classical hybrid computing. Wow, very interesting. He remains actively engaged in talent development and collaborative research under QCSP and other institutions, including part-time teaching roles. And yeah, his work has resulted in several peer-reviewed publications on quantum applications and education. And yeah, he has presented his research across Asia and North America. So yeah, he's also the author of multiple quantum research initiatives here in the Philippines. So you might have heard or might have seen the posts there with a total of funding of over 700,000 US dollars. So again, let's give a warm virtual applause to Sir Dylan Josh Lopez. Woo!
Yeah, thank you for that, Jabez. So hi everyone. So hope you can hear me well. So if you can't hear me, just raise your hand, and I'll try to raise my voice a bit. Okay. So thank you for having me. So allow me to share my screen. Uh, Actually, I changed a bit of the slides based on your answers in Menti. Since most of you like AI, so I put a bit of AI in our presentation for today. Okay. So I think. Okay, we're good. Right. So, welcome to the first of our sessions on quantum technology in ICT in the National ICT Month. So, Digital Bayanihan is our theme. So, one of the themes that we're going to present under the Quantum Computing Society is how do we do Bayanihan with quantum computing. So later on, I'm going to show you how do we build this in our own tech community in the Philippines. But for now, I want you to see what would be the future of ICT, especially in the Philippines. Okay, so if you have any questions along the discussions, please do ask them. Jabez will be out in a bit, so I'll be handling your Q&A. So I'd love to answer them later. Okay, so let's go right away. So for today, I'm going to talk about a bit of what is quantum technology. Okay, what is quantum IT or what is quantum computing? There's also a thing as quantum communications or quantum communication technology. And how do we see or how do we expect ICT and quantum to evolve in the next few years? Okay. And of course, how do we see that in the Philippines? So, coming from our perspective as an NGO as well as a researcher and part of industry, what innovations are we expecting or what do we see in the industry in the next few years? Okay. So let's start. Let's review what is quantum tech. So for those who don't know what quantum tech is, that's completely fine. So in the very basic, these are devices, these are general technologies that uses the principle of quantum mechanics. So you don't have to dwell too much on the quantum physics right now unless you're a physicist. But the idea here, it's working with closely with the principles of nature as much as possible. Okay. So these works in very specialized states. Okay. So this is what we call in the quantum state. Some of them might need to be cooled near 0 Kelvin. Some of them needs to work as photons. Okay, in a very particle level, all of that very high level physics stuff. But we can enjoy these technologies, and we have three key technologies in quantum technology. Okay, there's quantum sensing, quantum computing and simulation, and quantum communications. Okay, so we're going to discuss today more on quantum computing and simulation and quantum communication. So in quantum sensing, we're just going to discuss this a bit, is creating new types of sensors that would observe some properties in the real world that can only be observed in the quantum sense, or even in the particle or light sense or photon sense. So we have one of the best examples is at our atom clocks. How do we synchronize and have precise timing in everything? There's also what we call gravimeters, is how do we measure fluctuations in gravity, and this has very good applications. So it's used to identify the gravity, the strength of gravity on Earth, and that will tell you the status of the whole aspect of the Earth in terms of its orbit. That's one of them. And another one is to determine disturbances in gravitational fields. And that could tell you where are certain objects in underground. Some of them would be oil reserves, okay? So we can identify where they are, even though we don't have to drill, okay? We don't have to drill soil, okay? We also have photons, a single photon detectors. We're going to discuss more on that later. It actually is more of a communication type of device. Okay. In quantum computing simulation, this is, I think, where you hear all of the hype, is how do we make the quantum computers? So we make quantum computers using several types of technology. It could be using photons, it could be using electrons, ions, or even whole atoms. Okay, and we can embed information onto those objects, or what we call quantum objects. Okay, and we simulate them with nature. Okay, the whole course of the whole, or the natural state of quantum mechanics. Okay, and there's also quantum communications. How do we transmit information, those kinds of information, through a network? How do we create a new type of internet, which is what we call the quantum internet? Okay, so we're going to discuss some of these technologies and how does that relate to ICT. In this case, we're talking about software and some of the mostly hardware for today. For some software, such as AI, we're going to talk about that a bit later. Added some new slides if that allows in our time for today. So we're going to talk about, there is a topic called quantum machine learning. So we're going to, do a teaser about that, because that's a completely different session we had with Computing Society of the Philippines last time. Okay, so there is also a sense of quantum information science. Okay, so how do we use all of these information produced in the quantum realm, or using the quantum mechanical way, and how do we take advantage of that, okay, in terms of different disciplines? So there's quantum sensing that has quantum sensors. How do we use that in a quantum internet, or transmit that in a quantum internet? How do we make quantum computer systems that would interpret those information? How do we utilize those how do we create applications on top of these quantum computers using quantum algorithms to make something useful, such as quantum AI? There is also quantum optimization that gives us a hint that there is a way to improve data science using quantum technology. Okay, and there's also, for those very interested in security, there is quantum cryptography. Okay, so this will now have advancements in the cybersecurity space. Okay, oops, sorry, a bit. So a bit of background. Okay, is Moore's law. Okay, so we're gonna go into the idea of computing, or why do we even need to have quantum technologies for ICT? So for those who understand or know Moore's law, it's more of an observation wherein the number of transistors in an IC double per year. But this has already been broken for the past decade, because we're cramming more, not just double but 10 times of IC all of these transistors in an IC circuit. Okay, but there is a question of how much can we cram into an IC. Okay, so that leads us to the idea of quantum computing. So one of them is, if we try to make all of these designs, all of these circuit designs, smaller and smaller, they tend to become, well, very small and in the nanometer scale. And if you are in the nanometers scale, that could lead to some complications later. If you go even beyond the nanometer, especially if you go beyond, there could be some complications. Okay, So that complication is rooted from quantum mechanics. Okay, so if you have an electron and it's passing through a wire, if you have a very copper wire right now, it just informs electricity. That's cool, and that's the very basis of information transfer, switching theory in electronics. But what if you make all of those wires super thin that it's almost to the size to an electron? Now that's going to be give some complications in design, because in quantum mechanics there is what we call a phenomena called quantum tunneling. Okay, so in quantum tunneling, instead of an electron passing through a conductor, and there is insulations. Now, if that insulation, such as air or any type of plastic that's surrounding that, it could jump. Okay, it's not just going to bounce from within the bounds of the insulation, but it can actually pass through. Okay, and passing through that, there is a probability. Again, there is a probability. Instead of bouncing, it's going to go through your insulation, probably going to another wire. And we don't want that in terms of switching, because the amount of electrons required to activate a certain device might not be enough, or it's activating something else in the whole circuit. Okay, so that's a problem. Okay, so that's a concern that we need to look at if we are going to design. So one way is to have to have a constant size of these circuits, or another way is try to find a new way of computing, and that is quantum. Okay, let me just do that. So the point here now is, if we look at information um, in the classical, or I'm going to use the term classical, anything that you know right now is classical. Anything that is not classical, which is in this presentation, we call that quantum. Okay, so in information representation in the classical sense, your bit, okay, the basic piece of information is encoded by electrical pulses. If it's high, 5 volts, it's on. If it's closed, or 0 volts, is 0. So that's a 1-0 encoding. Okay, that's your bit encoding. And for each point in time, it could only be one. It cannot be both 0 and 1 at the same time, because that's the point of your fluctuations of electricity. Okay, so at one point in time, it's 100% 1 and 100% 0. Okay, it's not something that you go in between, because if you try to activate a certain semiconductor, there is a threshold. If you go beyond that, it becomes 1. You go below that, that's 0. Okay, that's how it works. However, what if we can do a different way of encoding information? Okay, there is that quantum sense. Okay, and I'm gonna show you how this is possible in mathematically, also beyond the idea of on and off. So we scrap the idea of on and off in quantum computing or information representation. It's more of probability. Okay, how possible that it is in a state of 0, quote unquote 0, in state of 1. Okay, we don't label 0 and 1 as on and off right now. It's just 0 or 1, a position in space probably. Okay, so there is now a chance that it could be a probability of being in 0 and being at 1. Okay, so that might sound crazy, but mathematically there is a probability that you can be in between this. Some call it fuzzy, some call it probabilistic. In this case, it is probabilistic. We call that, some call them probabilistic bits, or p bits. Okay, but how do we realize the theoretical sense of p bits? Is using a quantum computer. Okay, so a quantum computer can encode all of this not as a pulse, a 0 or 1, a switch, but as a vector. Okay, if you're doing AI, you have heard of vectors at least once. And that means it's more than just one value. It's not an integer, it's not a floating value, it's not a float value, it's not a decimal, it's two, possibly at least two values in space. And that's complex, complex numbers. So there are more representations of showing being 1 and being 0. Okay, and that is giving about the idea of superposition. And in the sense of computing, it's also simulation of nature, simulation of quantum mechanics. Now, if you want to simulate anything that is quantum mechanical, you might physics physicists might argue that everything you see is can be related to quantum mechanics, and that's almost true. Actually, it's very true. So, for example, in material sciences, if you want to simulate states of matter, it's physics, quantum physics. If you want to simulate chemicals, or you want to test out all of those chemical bondings, or even in organic chemistry, all of them are represented somewhat in quantum mechanics as well. And if you want to simulate that, the best way to do that is using an actual quantum state. And that's something that's something that could be done in a quantum computer, not just in any type of regular computer. Okay, so that's quoting from what Richard Feynman said, if you know him. Okay, so all of these would become the new, or actually a new type of viewing information. Okay, that's the very basis of what we're going to talk about today. That information is not just pulses, it is now a vector, and that vector could be represented or embedded through an electron, an atom, an ion, a photon, all of those subatomic particles, not all of them, those parts of subatomic particles. Okay, could be embedded or could be used for embedding information. Okay, it's not just a stream of electrons, actually one electron. Okay, one electron can be encoded into such. So just like I said earlier, that your information, imagine an electron, a bit of round, like a round electron. You can imagine how it spins, and that spin points somewhere, either up, down, left, right, or any direction. And you can imagine how that would look like as a state. So a state now would tell you if it's 0 or 1. Okay. So you can imagine an angle. So because it's now a vector. Okay. So we can encode it as this. Okay, and we're not going. This is not a math class, so we're gonna skip this. But anyway, the idea is this: these are vectors, and these represent how information is. Okay, and encoding them, having an angle, having a direction. Okay, it's not just on and off. Okay, so we're gonna conceptualize this now in idea of a computer system. So I believe that all of us here are computer people. So I'm gonna try to relate that to you in what we call the computer system abstraction. So with designing computer system architectures or understanding computers, there are level of abstractions from the physics level to what you see right now. Okay, similar to the idea of an OSI model if you're doing networking or networks. So there is from the very basic level, the fundamental level, to like an application layer, something that you realize you see every day. So I'm going to do a comparison, a very strict comparison using a regular computer and a quantum computer. Okay, so the physics behind a classical computer is an electron. Actually, it's a stream of electrons. It's based on electronics and how electrons flow. Okay, your electricity. However, quantum computing or in quantum computers, it's more of the electron spin. In one of the technologies, it's an electron spin. Okay, and that electron spin encodes more information. Okay, so in a classical computer, one bit is one piece of information. Okay, one bit is to one bit. Okay, however, in a quantum computer, you can represent two bits in one what we call quantum bit or qubit. Okay, so imagine that. So for just one representation, it could represent two values, a 0 and 1 at the same, probably at the same time. Okay. So if you have two qubits, you have two more. So that's 2 times 2. So that's 4. So for 2 qubits, you have 4 classical bits. And if you have 3 qubits, that's going to be another, okay, you're going to multiply it again. So that's another 2. So it becomes 8. So the progression is for one piece or for one qubit, it represents 2. So that's a 2 raised to n comparison. Okay. So if you have more qubits, that means you have exponentially more representations in your classical bit. So that saves space. Okay, so that's one basic idea of the physics. In a classical computer, we have transistors. Okay, we have transistors, we have your gates. We also have that in a quantum computer, especially in a technology called superconducting quantum computers. We use this kind of transistor. We have Josephson junctions or J junctions, and we have couplers to have, controlling those qubits. Okay, so controlling a qubit, it differs in types of quantum computers. Some of them is controlled by microwaves. Some of them are controlled by radio frequencies, but some of them are controlled by light. So right now, it's more important to say that there is a control circuit, there is a qubit, and there is logic there that you can, control them into a certain angle that is the current state. Okay, so if you don't understand right now, it's completely fine. Okay, this is a very new technology and something that we can go along as it develops further. I think you have heard a similar thing with AI in the past years. Okay, so in a classical computer, we have a CPU, a central processing unit. In a quantum computer, we have a QPU, a quantum processing unit, because that quantum processing unit handles, encodes, and controls the qubits that you will use in computation. Okay. In logic design, so we have a circuit, you proceed now to have logic. And that could be in classical computers, we have your AND or NOR gates, combine them together. They form different types of other gates. You have sequential gates, you have other recurring gates. You can now create memory. Okay. We also have that in quantum computers. We have quantum gates, and those are represented something like this, like a staff in a musical, like a musical staff. But these are operations. Actually, these both serve as the same thing. If you are familiar what the circuit is, it's actually an adder circuit on the left, and also an adder circuit, a quantum adder circuit on the right. Okay. You also have computer architectures. In a classical computer, you might have your Princeton architecture, you have your von Neumann architecture. I think you know that. But also in a quantum computer, you have computer architectures. So we have quantum registers to store the memory of your quantum states. We have now measurement because we want to know what is the observed state of your electron, your atom, or your photon. And you have gates that you actually apply the gates onto the quantum objects so that they could move around and perform operations. And on top of that, we have assembly languages that, because we want to control specifically the movement of our registers, we have to move certain operations, do addition, subtraction. That's something that we do in classical computers. But in quantum computers, what we do is we try to do operations such as flipping, trying to have conditional flips. We do superposition to make them for one state here as 100% at this zero state. But sometimes we split them and we can observe both 0 and 1 at the same time. Okay. So we also have quantum assembly language. Then for computing, we now abstract this by using starting from a low-level language as a C++. So yeah, C++ can also be used in doing quantum programming. But on top of that, of course, you can use Python. So anything goes now. So if you have in your application layer or your computing software, you can now use different types of hardware, or rather different types of programming platforms to work with a quantum computer. Okay. So there's a lot. So these Qiskit, PennyLane, these are all based on Python, by the way. But we also have, I believe MATLAB can also do quantum programming already. Okay. So that's a just the street comparison of your classical computers and your quantum computers. Okay, cool. Ooh, let me just. Ooh. So one good example here is with Intel's full stack of quantum computing. So Intel uses a different type of technology called spin qubit processors. Okay, so we're not going to discuss the physics behind that, but it shows here what it does. So the QPU here, this is the actual quantum computer. All of these are just refrigeration. Okay. These are coolers. Okay. So all of the processing of the qubit is here. These are your circuits, so on. These are encoding the quantum states of a qubit, all of those electrons. Okay. We have your control chip. Okay. So if you recall, if you know your computer architecture, these are control units in regular computers, but these quantum computers also have control units. Then on top of that, we convert all of the readings from the quantum realm into the classical realm or the real world using observations, okay, or measurement circuits. And that those become now your classical bits. So we convert quantum information to classical information. That's now something that we can work with your regular electronics, such as your PCs. So it's not exactly that you have a laptop connected to your quantum computer via USB. No, it's usually interpreted into a different type of server or mainframe where you can access it using cloud technology. Okay. So, but if there are mainframes there that runs on C++ and quantum compilers, but so yeah. But again, if you're working on Python, these C++ libraries can be abstracted later on to have that interfacing with Python. So let's now proceed to the other part of ICT, which is well, the C part of ICT, the communications. So we have the information side. Let's move to communications and how do we meld them together. So it's best to understand this, if you're in the network's perspective, is to discuss the OSI. So if we look at the OSI model later on, is how do we have that from the physical layer until we have the application layer. So we'll see the street comparison again. Actually, it's more of the quantum aspect. So we'll start with the physical layer. So if we want to transport information using quantum technology, so the main idea is using light. Okay. So one of them, or actually the main technology right now, is using fiber optic networks. Okay. And there's also, well, another way to transmit this using line of sight, which is free space. So if you have, actually you can transmit this using telescopes, okay? But the idea of quantum networks is entanglement. So let me discuss entanglement a bit. So the idea of entanglement, if you have two electrons or two quantum objects or two qubits, as you say, and you try to meet two electrons together, perform a special operation, and you try to pull them apart, okay? And you pull them not just, a few centimeters away. You can pull them maybe one in America and one here in the Philippines. So what happens if you try to do an operation on one qubit, let's say you rotate that, there is a correlation wherein this also rotates, okay, without anything else interacting with it in any external environment. And so if you do another operation, it interacts, okay? So there are already experiments that did this already. One of them is through satellite communications in China. So they have a qubit on Earth, another one they send outer space, and then you try to do an operation one on Earth, and they observe that if you spin this around in this direction, this spun also in a different direction without anyone touching that qubit, that electron in outer space. Okay, so that's entanglement. Okay, so it's just like a very good way of communicating two different quantum bits. So we try to utilize that using these technologies. So either using terrestrial networks or fiber optics and free space, or using telescopes. So another one in the data link. So if we want to encode the information, so from any quantum device, you now encode them using this way. We call them BB84 protocol. Okay, so this would now be encoded using, well, different polarizations of light. So if you know what polarizations are, similar to those polarizing glasses. So some light gets in, some types of light do not. So for example, UV light does not go in certain directions, and some do. Okay, so that's how we encode this, and that will now be translated into a different type of a filtered or transformed quantum information. For the network layer, we have quantum repeaters. So these are running on actual hardware. These are not simulations on laptops. These are actual hardwares. So quantum repeaters. So since the entanglement is not absolute, okay, so it somehow dissipates through time. and distance. So we need to have repeaters similar to network repeaters. So we need to boost them again so that they could be, or segment the network so that it could be boosted so that it can reach to the other side more efficiently. Okay. And there's also quantum controllers because we want to control where it goes. So it's similar to the idea of having a router or switch. But all of these are running on FPGAs or quantum FPGAs. So that's both in transport and network layers because we want to retain the quality of the network through enhancing the entanglement. Okay. So that's also in the transport and session layer is entanglement purification. It's more of an implementation of a circuit. So this is actually a circuit, what you see on the screen, wherein we try to improve the quality of entangled states, so or the entanglement. Okay, so that when you receive it on the other end of a communication network, it's the same in quantum information that you got from the earlier from the source. In the presentation layer, we need to ensure that the information that you got, information sent is the same as information received. Now, that's a bit tricky in quantum communication networks, since even the slightest change of states, or let's say a filter, a polarization in a photon, could change a bit, could have a bit flip. That means you change, almost probably change a sign or change an information piece of information encoded. So there is what we call quantum error correction, and that is correcting the information, the quantum state based on your original data. Okay. Oops, sorry, move forward. And of course, there is security of your network and of data. So the realization of everything we saw so far is in the idea of quantum key distribution, or QKD. This is one of the new what we call quantum internet applications, wherein we send data from one point to another, ensuring that this is is protected or encrypted using a quantum system. Okay, that's the QKD system. Okay. So we're not going to dwell too much on this as a cybersecurity topic, but yeah, this is something that is being implemented already by the US, some parts of the EU as well, and I believe in Korea. So there are also other technologies, we call them as post-quantum cryptography, that also ensures the security of the network that could not be intercepted cannot be intercepted by quantum computers. So there is another algorithm that I forgot to mention here is what we call Shor's algorithm in quantum cryptography. So if you have heard of that, cool. But for those, let me give you a bit of a story of Shor's algorithm. Shor's algorithm is one of the most famous algorithms out there that could be realized in a quantum computer. And there is another piece at play. It's called RSA encryption. Okay. RSA encryption is the most pervasive cryptography we have right now because it takes a lot of time for a classical computer to solve it. So they mentioned that if you have a certain length of a password or a length of an encryption, it could take you about 7 million years to solve it using a regular computer, even the best HPCs out there. But if you use a quantum computer, theoretically, it could solve it faster than a classical computer in a very exponential improvement. So instead of having a 7 million years to crack information, it could probably take 7 seconds, 7 minutes instead. And that is amazing and scary at the same time using the powers of quantum computing. So to counter that, we need to have different cases. So one of them is using post-quantum cryptography. So that's something is another trending topic, or actually an emerging topic in security systems. Then lastly, if you have your application layer, this is realizing it on a quantum computer. So similar to what we have discussed earlier in the quantum security system, quantum computer system, it now goes to that application layer on how you can use it for different algorithms. You can use it now for, let's say, database search, quantum machine learning, optimization, even some parts of data science. So you can do that now. And it can now be received by a quantum computer. Okay. So that is the main idea of putting them, or actually having the I and a C together. If you combine them, having the quantum computer in place, you complete the whole ICT framework. Okay, so if you can, stitch all of these idea already, this now gives you the idea of how a quantum ICT framework works. Okay, so all of the parts, as you know right now, from our most vital parts in an ICT framework could be done or could be augmented by quantum. Now, there also exists that it could be done using what we call hybrid. You have your current systems right now, and you can augment them with quantum computers or quantum devices. Actually, there's another part here I forgot to mention, is the quantum random number generator. The quantum random number generator is actually very vital in the QKD system as well if you want to enrich the randomness or the entropy of a certain number. Okay, or we have your key here. Okay, your private key. So using quantum mechanics, you can quote unquote improve the quality. Actually, yeah, no quotes there. So improve the quality of randomness of a number. So the true quotes here lie in the true randomness. Okay, so it's still arguable still arguable on which metrics QRNGs would have to know the quality of randomness. But then again, it's still random due to the nature of quantum mechanics. So it uses the power of quantum mechanics to ensure that there is randomness. There's no bias in the network. Okay. So I'll show you a bit of the futures of IT infrastructures. So there could be a local deployment, just as a very high performance computing installation, where you have your CPUs, you have your GPUs, and a quantum computing device. Okay, so this could be your quantum computer. There's also a distributed HPC method, wherein you have your CPU, GPU, and the quantum computing device, and you can distribute loads of information using different CPU, GPU clusters. Okay. There's also hybrid quantum devices. So there are actually more than one type of quantum computers, quantum computing devices. There's a quantum annealer, for example, that's very good for combinatorial optimization, such as traveling salesman. And you can combine that with a QPU. A QPU is your any type of quantum computer, or what we call universal quantum computers, that can do encryption, that can do quantum machine learning, database searches, simulation, so on and so forth. And you can combine them with a CPU GPU cluster. There's also another one, which is the federated machine learning, or this centralized quantum and distributed computing, wherein you have a centralized quantum computing device and you have different CPU and GPU devices, clusters deployed and connected to a central device. Okay. So you can see all of these combinations together. And one of the early adopters, I believe, of this is Hewlett Packard Enterprises. So they have also proposed their own hybrid quantum IT infrastructures with this just recently this March at NVIDIA GTC. So actually, not just HPE. I believe Fujitsu has also shown their infrastructure here, and of course NVIDIA, that shows their partners how to combine all of these CPU GPU clusters with quantum computers. Okay. So how about in the Philippines? So right here, right now, I believe that you are one of the starting people of understanding quantum ICT, and that's really cool. Okay. And this is very cool for you as well, because you probably are the pioneers of quantum ICT in the Philippines. But let's try to understand, is there an investment in the Philippines in quantum computing? The answer is yes. The government has allocated budget for quantum technology development in the research sector around $15.3 million. That's 850 million pesos. And that's cool for having a budget, but it's not cool because we're not fully utilizing all of those budgets yet, because we lack people that could use the budget or actually ask for the money. Okay. So it's a really good time right now that you guys are trying to learn about quantum computing, quantum ICT, and how do we realize it in the Philippines. So support is ready. So we in the Quantum Computing Society would really love to support you guys in doing quantum technology. And of course, the government is very willing to help as well. Okay, so I believe there's also efforts in the ICT on doing quantum technologies in the future. But talking in the UST perspective, so I mainly work with UST nowadays and DTI. But in the UST, we have the quantum technology roadmap already. This was already launched a few years back already. But again, the development of this is well, ongoing as well. But it's never too late for you guys to get into the roadmap because we're in the progress, but we're still far away in realizing a fully blown quantum ecosystem in the country. But the real players that would realize this, it's not just the government, it's not just the academe, but it's also industry. But what's better is that everyone in the industry, academia, and government working together in moving forward in developing a quantum ecosystem, a quantum economy for the country. So, so that's it. I am really calling for everyone to try doing this. It's not just theory, especially in quantum communication. This is a lot of industries in the European Union and the Americas are already doing quantum communications, even in satellite communications. So I just want to reiterate what Jabez presented earlier. So we are the Quantum Computing Society of the Philippines. We love to help you guys if you want to get into quantum technology. We can connect you to the experts within our organization, even outside the country, to do collaboration, to do talent development, and really promote what is quantum technology and what it means for you and for the country. So I'm also going to invite you guys. We're going to have the 𝐃𝐢𝐠𝐢𝐭𝐚𝐥 or Quantum Information Science and Technology Conference in the Philippines this July to August 1, just the week after the AI-Con. So it's okay if you can't go to Mactan, Cebu. It would be fun if you're there. But we're opening this to the public via online. So we are going to send out invitations to everyone who's interested. Registrations will be open very soon for public viewing. And this is completely free if you want to join us online and to see how quantum technology will be developed in the Philippines. So we're going to invite several stakeholders from different parts of the globe, from the US, the EU, a lot from the Southeast Asian region, Singapore, to present their works on quantum technology and even hopefully convince our industries and government sectors during the event. So we're also going to do some workshops as well on quantum technology and quantum policy development in the Philippines. Quantum education, if you are also fond of doing that. So we're opening these in the next few days, so please watch out for that. But if you're interested solely on learning quantum in the long term, so please just send us a message in our Facebook group. So it's not here, but you can search us at the Quantum Computing Society of the Philippines and express your interest. Right now, we haven't opened public registration for our groups yet, but it will be soon in the next few months. So registration for membership, formal membership, will be in the next few months. So if you want to know more about quantum, have regular trainings on quantum technology, we'll be opening our doors to you. But if you have questions for mentorships, you can directly ask me through, well, if you can find me on LinkedIn anyway, or you can ask through the Quantum Society's page. I would love to help you out, especially if you're doing research. We really need to do research. If you're still undergraduate, that's completely fine. I have seen a lot of undergraduate researchers doing quantum technology, quantum computing already in the last few years in and outside the country. And, you just need to have the courage to do so and the right guidance. So we can provide you some of the right guidance. We have already some interns before doing quantum computing. So that's fun. Okay. Thank you. But okay, since this is, I'll give you a bonus. We have just a bit of time. I saw that you have interests in doing AI. Just a sharing. I'm also a member of AAP, and I'd love to share this to you if you're also a member. I'll give you a bit of a teaser on quantum machine learning. So a bit of background. So if you have ML, it's just cramming all of those data and encoding it as a vector later on. ML as an encoder produces vectors. Okay. And those vectors, well, are just representations of anything that you have right now. So if you are familiar with LLMs, these are what we call embeddings, or general or Gen AI. So technically, ML is just an encoder that spits out, enters a vector, it spits out another vector. Okay. And those vectors are all in the real space. Okay. float numbers, negative integers, so on and so forth. So they're limited, and you need to put that in storage. So if you want to have diversification of your data, you need to have more storage. Okay. Now let's try to review the idea of quantum information. That if you have more of information in a classical sense, that means you can represent it a bit less, actually exponentially less in a quantum space. So you can represent more information of your vectors in QML more efficiently. That's one advantage. Second advantage, if you're encoding vectors from machine learning, it's also again in the real space. So you're just representing one aspect, okay? One view perspective of a certain topic. But in a quantum ML, that means you have more information, extracting it also in the imaginary space. If you have complex numbers, you have a real and imaginary space, right? So normal ML would extract information only in the real space, not in the imaginary space. But if you have quantum machine learning, it could extract it in imaginary space as well. That means you have enriched feature extraction in quantum machine learning. So we did research at my university. This is all on 172 journals, both in Science Direct, Elsevier, and IEEE. And the top industries right now that are researching or doing research on quantum QML is in the field of networks and ICT. Okay, different aspects, communication. There's also spanning it in security and so on and so forth. There's also in health, remote sensing, space technology, and the energy sector, and so on and so forth. But if you're looking at technology applications, the number one technology application that uses QML right now in emerging tech is computer vision. The next would be anomaly detection, so on and so forth. So yes, quantum computing is also applicable in machine learning, hence in data science as well. So that's the bonus part, right? I hope you have any questions. So I think that's it. Thank you guys for listening. So I just want to have a message to you from Jabez. So you'll be receiving emails for your certificate of participation based on your Zoom stats as well. So I think that's in the duration of your stay. So yeah, thank you guys for listening. So if you have any questions, I'll be happy to entertain them. Just stop sharing my screen for a while. Okay, let me just open the chat for everyone. Yeah, sure. I'd love to connect you on LinkedIn. So just send me an invite. So if you don't have any question, I'll ask the questions. No, just joking. This is not a class. Right? Any questions, guys? Clarifications, violent reactions. Okay. Let me see. Do I have the most frequently asked questions on quantum machine learning is how can we do it? You can do quantum simulation using regular CPUs and GPUs, by the way. So if you already know Python, that's very easy to do it already in your regular computers. There's also cloud access to quantum computers, so you can try them out. So one of the best quantum education sites, quantum resources out there is from IBM, IBM Quantum. So you can search that. Yes. Yeah, quantum computing is really, right now is one of the futures of tech. Okay. And I'm not saying it's the only future, but it's one of the people perceive it as the somehow realizable future of technology. So question here from Vincent. So quantum entanglement will be the main quantum function that will be mainly utilized in telecommunications. Yes. Well, I'm not saying that it's mainly the communication medium. However, it could be an augmentation to the current telecommunication media that we have right now. So currently we still have fiber optics anyway, but it could be one way to improve this. So one of them is creating a more reliable VPN using quantum internet. Okay, so we cannot see in the next 5 years that whether quantum technologies will be the basis of quantum internet working, but it is implementable in our current systems. Questions: are there countries that are already advanced in applying quantum tech already? Yes. So number one is China, of course, in terms of patenting. If you check out the patent literature as well, China has been leading. Next is well, together with the U.S., the European Union are already commercializing quantum communications. So there are a lot of QKD startups already. Quantum computers, there are a lot of industries. So we are inviting some of them in our KIST conference. Okay. So how about the Philippines? No, no, we don't have any industries, but we have a lot of researchers. So we have in different institutions already, but it is something that we are really wishing that our industries would adopt. That's something that we are aiming to do during the conference to entice our industry to adopt quantum technology such as communications. So I have a question from Mark. On quantum side for pre-processing, then ML models for training. That's a one perspective. Okay, I'll just clarify that this is on QML. So yes, that's one perspective of looking at it. So there is quantum, what we call quantum embeddings. So how do we process quantum computing, quantum information for quantum computing, then transfer that for machine learning. So that's one way to do that. There's another way. We call that if you're really specific on ML or specific on deep learning, you can actually customize a neural network where in one of the layers of a neural network are all qubits. That means you have a quantum neural network within a deep neural network. That's what we call hybrid quantum neural networks. So that's one way. So there's another way wherein you use machine learning to improve quantum computers. So that's a different type of machine learning aspect. So there's hybridized quantum computing, there is QML ML, there's ML QML applications. So what, again from Vincent, what are my thoughts on future edge and telecom that will be run on quantum teleportation? That's something I did not discuss today on quantum teleportation. So let me discuss a bit of how it works. So quantum teleportation is not just what you imagine in Star Trek, that you beam me up, Scotty, and information just vanishes. There is the concept like that, but not exactly. So imagine like this: you have 2 points in space, one probably here in the Philippines, another one, or should I say Luzon, another one in Davao, sorry, Manila, and one in Davao. Okay, so information, the qubit holds information. They're placed in Manila, another qubit in Davao. So if I encode information right here, I have a vector representing the word hello in my qubit. So quantum teleportation works as you need to destroy the information here, it vanishes, then it reappears in Davao's qubit. Okay, so that happens using a specialized preparation that also includes entanglement and superposition. Then that works later on. So quantum teleportation compared to entanglement in QKD is something that we expect in the future, but it's compared to entanglement networks right now, it's more realizable to see fiber optic networks with quantum entanglements rather than having teleportation devices. Although quantum teleportation devices already exist, where it's not commercialized so that you can use it in the industries yet. Okay. For another question from Ariel, our respective text fields right now. If you want to reach quantum computing for the quantum QCSP, I believe, what could be the first step, or generally quantum computing? What's the first step to include our plans to learn about it and apply it in our careers? So let's divide that question into two. First is, okay, no, three: learn, apply, and careers. So I'll talk about learning first. Number one thing is one big demystification is you don't have to master quantum mechanics for learning quantum computing or quantum tech. Yes, quantum computing, not exactly. Physicists might argue this, but this is based on experience. You can still work on quantum computing methods without exactly learning all of the quantum mechanics 1 and 2 from university physics, unless you want to work as quantum engineers or quantum electronic engineers, wherein you want to create all of those devices. Of course, you need quantum physics. But if you want to do programming, quantum programming, you might just need the concepts of quantum mechanics, not exactly how to solve all of those differential equations. But what's mainly important is learning linear algebra. All of those algorithms run on the idea of linear algebra. And for those who are learning AI, you might have noticed that it is not exactly required right now, but it's really important to know the idea of vectors and linear algebra if you want to know deeper about machine learning or deep learning in specifics. Okay, so that's one thing. You need to learn about some of the math. Programming, if you already know Python, that's completely fine. But again, number one is linear algebra. So that's learning. Next is the idea of getting a career. So right now, we don't have a market in the Philippines. Not yet. Hopefully we do. But in the regions, we do have markets of quantum engineers, computer scientists, quantum IT already. So some of them in Australia, Singapore, and in the European area. So yeah, if you want to plan a career for quantum, so I do suggest start with something classical. So if you're working in IT, let's say in information systems, please do. But keep in mind that in the future, there will be quantum. So if you're in the management level, you need to put it at the back of your mind, or even actually also in the middle, that quantum computing might disrupt some of the technologies we have right now, or it is essential for it to augment current systems. Okay, so the community or us in quantum computing society would love to help you prepare for that in different levels. If you're just student, if you're in management, if you're in a career currently in your career, we have different levels of how do we improve or augment quantum in your classical knowledge. So yeah. Do we have any more questions? Okay. Hope you guys would do some, you want to do quantum research. That's completely cool. Computer science, yes. Very cool. Right. If you don't have any questions or you don't have any right now, you can send us a message later on. I'll try to leave my email here so you can send me a message. Mm, Yes. So here's my email. Send this to all. So you can send me an email if your institution would also love to partner with the Quantum Computing Society. We do offer. I think you did not show this earlier. We offer specialized trainings for institutions for quantum computing. So if you have your cohort, your batchmates, or faculty members that wants to have training in quantum computing technology or any specific quantum tech, we can arrange that for you. We have did several already in the past few years with Bulacan State University, Pangasinan State University, TI Technological Institute of the Philippines, and so on and so forth. So if you also want to do that, that's something that's on the table. So we would love to collaborate on that as well. Internships, I believe we do have internships in the next few months. So probably after August, because right now it's quite busy. But yes, we do accept. Actually, we had two students already from the Cebu Institute of Technology as quantum computing interns last year. So if you're also interested in that, we can try to have a collaboration with university to have probably an MOU. Okay. So yeah, if we don't have any questions, if you want to ask questions via email, I'd love to connect with you. So if nothing else, thank you guys and see you tomorrow if you're interested. So we're gonna have a demo using NVIDIA CUDA Quantum, one of the Python packages for hybrid quantum machine learning. So I'll be demonstrating some of those applications and a bit of the idea of QML. Those slides that you saw earlier were supposed to be for tomorrow, but since you are interested in that, so I'd love to share that to you again tomorrow. So if anywho, see you tomorrow on the demonstration on hybrid quantum machine learning. So thank you guys and bye-bye.